Hi, it's going to be my job to show you arithmetic series, geometric series, and then the difference between divergent and convergent, which is found within series. So with that being said, the first thing I'm going to show you, or tell you, sorry, is the definition of a series. So a series is merely the sum of some terms, and that sum could be all, could be none, could be 3, could be 4, but it's the sum of some terms, okay, in an arithmetic sequence, which is what Mr. Duncan showed you. Okay, so if you add up all of those numbers, then you end up with a sum, and so that is called a series. You can only take a partial sum, which means just a few of them. Well, it could be a lot, but still not all of them. Of a finite number of terms. All right, what does this mean? Finite means that there is an end, okay? So if you have a series, which is arithmetic, so you're adding, let's just, for instance, say the odd numbers, 1, 3, 5, 7, 9. Well, if I asked you to take the sum of the entire series, 1 plus 3 plus 5 plus 7 plus 9 plus ... the answer would obviously be infinity because the numbers keep increasing, and so would the sum. So you can only have a sum answer, all right, which would be a partial sum, if you gave me a specific number of terms to add. Finite, meaning an end. So if I said only add the first 5 terms, well, you could give me a sum. 1 plus 3 plus 5 plus 7 plus 9, that would give you an actual answer. That answer would be 9 plus 7 is 16, plus 5 is 21, plus 3 is 24, plus 1 is 25. Okay. So let me show you the trick that was discovered long ago, but it's a really neat trick. And that's taking any sort of arithmetic series. So A1, A2, A3, all the way up to AN. And we don't know how N is. But it's really cool that if you write the sequence forwards and backwards and then add the corresponding elements, you can actually figure out the sum of the entire sequence. So let's take this example 1, 3, 5, 7, and 9, okay? So I'm going to say that A1 is 1, and that A2 is 3, A3 is 5, A4 is 7, and A5 is 9. All right. What I'm going to do now is I'm going to write them backwards. So I'm going to say that A1 is now 9, A2 is 7, A3 is 5, A4 is 3, and lastly, A5 is 1. The neat thing here, look at the sum of each of the corresponding elements. 1 plus 9, 3 plus 7, 5 plus 5, 7 plus 3, and 9 plus 1. Hopefully by now you've noticed that all of those are the same sum. They all have an individual sum of 10. Well, how does this help us? Well, I know how many terms I had, which was 5 of them. So really, I have 5 tens. Cool. So that makes 50. But I really don't have 5 tens. I have half of that. Why do I have half of that? Well, I wrote the list twice, so if I want the sum of the original one, it's going to be half of that. So I'm going to divide this by 2. And so that answer is 25. Well, I'll be. That's exactly the same answer that we just got previously when I added those numbers. 9 plus 7 is 16, plus 5 is 21, plus 3 is 24, plus 1 is 25. So 25 checks out to be our answer. So how do we write this mathematically in a formula? Because formulas are good that we can plug into them later for any other problem. Well, what's really interesting with a series is that it includes another way to write this. Instead of saying 1 plus 3 plus 5 plus 7 plus 9 equals 5 times 10 over 2, which equals 25, I've got another way. And I'm going to show you that right now. So as I clear this and I make room for a brand new piece of paper. In math, we use the Greek letters a lot. And so this is the Greek letter sigma. And it represents the sum, or as we've been saying, series. So instead of writing 1 plus 3 plus 5 plus 7 plus 9, I can just say the sum of that sequence. Well, I'd need to know what the sequence is. And so we have a sub n here, which is a representation of the sequence. Okay, so that's the sequence definition. Here is the starting value. That's which term we're going to start at. Okay, and here is n, and that's the term we're going to end at. So this says, add up this sequence from x to n, or the x term to the nth term. Let me go back and show you what I mean. 1 plus 3 plus 5 plus 7 plus 9. If I were to write this sequence, I would say, as Mr. Duncan taught you last week, my first value is 1, and I'm adding 2 every time before 1. So that gives me 1 plus 2n minus 2, which gives me 2n minus 1. So this is my nth term definition. An nth term definition gives me how to create each one of these sequences. Each one of these terms. If I put 1 in, I get my first term 1. If I put 2 in, I get my second term 3. If I put 3 in, I get my third term 5, and so on and so forth. So it's this definition that you've already learned that we will plug into that notation. So 1 plus 3 plus 5 plus 7 plus 9 equals, another way you can write that is the sum of 2i minus 1 if we start at the first term and go to the fifth term. Those are the exact same thing. One written out long in its expanded form and one written in its simple form. It may not look simpler, but if I were to write the expanded form out for 99 terms, this would definitely be shorter. And then I go and write the formula beside it, which says, now I'm going to go and do this now in a different color. And it says to take however many terms there are, divided by 2, and multiply that by the first term and the last term. So if we go back and look at this, 1 plus 9, that gave us 10. And it was that 10 that we multiplied over and over. Why do I do n minus x plus 1? Well, if I told you to start at the fifth term, start at the first term and go to the fifth term, everybody knows that's 5 numbers. But what if I told you to start at the third term and go to the 10th term? You may think that that's 7, but it's not 7 terms. It's 8 terms because the 3 is included. Well, the only way to get there is to do 10 minus 3 and then add that 1. So that's why the base formula has the plus 1 in it. So let me go ahead and fill out that formula for our 1 plus 3 plus 5 plus 7 plus 9. I have 5 minus 1. There's my 5. And there's my 1. I add 1. I divide by 2. And I multiply by the 1 being stuck in there. So 2 times 1 minus 1, which is 1. And the 5 being placed in there. 2 times 5 is 10 minus 1 is 9. I can then shortcut that formula even again and say the sum of 5 terms is equal to 25. That's the way summation formula works, is written, and then is evaluated. We're going to do some examples now. The first example is to find the 35th partial sum of a sequence 1/2 n plus 1. I'm going to start by writing that in sigma notation. Sigma notation, it says the 35th partial sum. I hear that to mean from the first to the 35th term. The sequence that I'm adding is already given us in representation as a 1/2 I plus 1. Ms. Whitehurst, why do you use I? Well, the reason I use I instead of n, if you remember in our sigma formula, the bottom was x and the top was n. I represents all of those values from 1 to 35 and not just one specific one. All right, and then I'm going to complete my formula. I know that it's n, which is the top number, minus x, which is the bottom number, plus 1 to account for the number in between, divided by 2, and multiplied by the first number, which means you can take 1 and put it into this formula. So 1/2 plus 1 is 1/2. And then take 35 and put it into this formula. Half of 35 is 17.5 plus 1. And there we have it. The 35th partial sum, as I write S35, is equal to, and I'll do this in my calculator, 18 plus 1 is 19, that's 20. Half of 20 is 10. 35 and 10 is 350. So the partial sum is 350 if I were to add up these numbers. Again, you could have written it like, well, we know the first number to be 1.5 plus, we're adding a half each time, so 2 plus 2.5 plus 3 plus 3.5 plus ... and 35 times. But I obviously don't want to write that, so that's why I have my sigma notation. The next one, it's already given to us in sigma notation. Now they do use the value of n on the base. I'm just going to rewrite that because that's the way I prefer to see it in my eyes, but it doesn't matter as long as it finishes the formula at the end. So I am going to add from the 15th index all the way to the 47th. And the formula for the sequence is 2i minus 5. All right, here's where that plus 1 comes in. We're going to have 47 minus 15 terms. It looks like it would be 32, but it's not. It's actually 33 because we have to include the 15. But we're going to take half of those because remember, when we're adding the sequences forwards and backwards, we had to divide by 2 for the formula to work. I'm going to plug in my 15, so that's 30 minus 5, which is 25. And I'm going to plug in my 47, which is 94 minus 5 is 89. 80, 94, wait a minute. That's 80 and 14 is 94 minus 5, 89. Perfect. And again, I'll shortcut that to say the sum, and watch this. I'm going to do 15 comma 47 to recognize the first and the last terms that I'm including. And then I get my answer. 114 divided by 2, which is 57. And 57 times 33. 57 times 33. So that's 150 and 21 to 171. 171 with a 0 and 171. So the answer is 1881. Check my work, and yes, I did that correctly. So there is the sum for those problems. Okay, so there is a partial sum from the 1st to the 35th, a partial sum from the 15th to the 47th, and now what I'm going to do is other examples, numbers 3 and numbers 4. So for example number 3, it asks for the value of n. What happens is they've given you the sequence definition. They've also given you that it starts at the first term. And they've given you that the entire sum is 21. But what they haven't given you is how many terms it takes to add up to that. Yes, you could simply fill out this formula and plug it in for 1 and 2 and 3 and 4 and add them all up until you get 21, and you'll have your answer to figure out how many terms. But I'm going to show you how to use the formula and work backwards. Because in essence, this unit truly is just reading formulas and using them to find out all of the variables, not just the one on the right-hand side of the equal sign. All right, so I'm going to rewrite this number 3 the way I have been doing. I like the I to the N, but I'm going to rewrite it with the formula on the right-hand side. So I'm going to take my sigma, I equals 1 to N, because I don't know it, of my sequence definition. And remember, the formula is n minus x plus 1. So this is n minus 1 plus 1 over 2. And then remember, we plug in the 1 and then we plug in the n. If I plug in the 1, I get 2.25. And if I plug in the n, I get 0.25n plus 2. So I'm really just using the same formula, but now I have a variable. The problem told us that the sum was 21. So I am going to write this, that the sum of these n terms is 21. Well, somehow I had to get from this expression to this expression. So that means they are equivalent expressions. So what I'm going to do is I'm going to simplify this one and set it equal to 21 because it is the same thing. So I have n over 2, make sure you can see that, n over 2 times 0.25n plus 4.25 is all equal to 21. So I'm just simplifying here, trying to solve for n, which is something you would have done in your previous 3 math classes. Just get n by itself. All right, the first thing I don't like is this 2, so I'm going to get rid of it by multiplying by 2. Next thing I'm going to do is distribute this n to get rid of my parentheses. So I end up with 0.25n squared plus 4.25n. And then I'm going to bring all of this over to the left-hand side, which would be negative 42, to set it equal to 0, which is what we've always done with quadratics, that's n squared, in order to solve for n. We always set them equal to 0. So let's keep going. What else don't we like? Well, now we don't like the 0.25, so I'm going to divide every single thing by 0.25. I'm allowed, because it's an equation, that I can do it on the left and the right. So I end up with n squared plus, well, 4 quarters and $1, and that's $4.25, so that's 17. 4 quarters and $1, and that's 42, so 4 times 42 is 168, is equal to 0. So now I have a quadratic that we used to come up with the old standard way of factoring. N and n. And I need to think of 2 things that multiply to give me 168 and add together to give me 17. So I'm going to look at the factors of 168. When I look at the factors of 168, I'm going to start with the smallest one, which is 2, and that's 2 times 84. Well, 2 and 84 definitely don't make 17. So what I'm going to do is I'm going to divide the 84 by 2 and multiply it on the other side. So that gives me 4 and 42. That still doesn't give me 17. I'm going to divide it by 2 again, multiplying it by on the other side. So that's 8 times 21. Ooh, that's getting close. But that makes 29 or 13. That's it. Okay, 21. Well, inside of 21 is a 3, so I'm going to divide that on the other side and multiply it here. So that's 24 and 7. And haha, that gives me 17. Remember, one of them had to be negative and positive because of this negative 168. So I can say plus 24 and minus 7, which gives me a value of 17 when added and a value of negative 168 when multiplied. And I'm not sure if you remember this, but based on this quadratic formula and this factoring, I can say that the possibilities of n are negative 24 and 7. Okay, let's go back to the original problem. Remember, as I said, you could plug in 1 or 2 and 3 and 4 and keep plugging them in and adding them up to see if you get a sum of 21. Well, these 2 numbers are the possibilities of what n could be. Negative 24 terms or 7 terms? I'm pretty sure you know which one of those is meaningful. It's not negative 24, but it's 7. So if I had 7 terms in this original sequence, those would add up to 21. If you don't believe me, let's take a look at it this way. Plugging in 1, I have that the first term would be 2.25. The second term, the third term, the fourth, fifth, sixth, and seventh terms. Because remember, I just found out n was the value of 7. So the second term, put a 2 in there, that's 2.5, then 2.75, then 3, because I'm adding 0.25 every time, 3.25, 3.5, and 3.75. If I add those together, I get 2, 4, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. And then I get 19 and 20 and 21. So I do end up with the sum of 21, which is 7 terms. Okay. So it all falls back to the same formula. And I'm going to write that formula one more time before I start over with number 4. The formula is that if I start at an index value of something and go all the way to another index value inside of a sequence, I can add them all up by taking the number of how many terms there are, dividing it by 2, and then I multiply that by the first term given and the last term given and their sum. And that's the formula I'm going to keep going on with a series. So I'm going to erase what I have here, and I'm going to go on to problem number 4. Now, number 4 says, can you find the sum of these numbers? Okay, I know, I understand that you guys can definitely take the numbers 1 plus 5 plus 9 plus keep going, and you can eventually in your calculator figure out what the sum is. Okay, I'm not opposed to your doing that. However, that's only going to give you the answer, and it's not going to actually train your brain to use this formula. So let's try using this formula. When we start out with a sigma notation, we have to recognize which term we're starting with and which one they're going to end with. Well, right now, I don't know that this is not the first term, so I'm going to assume that it's the first term. I will always assume that unless being told otherwise. The next thing I need is which term I stop at. Well, I don't know. Not yet, anyhow. So I'm just going to leave that as a place value of n. I then need the sequence definition. So I'm going to come over on the other side and write this sequence definition for myself. So any term in this sequence starts out with 1 and adds 4 a bunch of times. Just subtract 1 because you already started with the first term. Distributing this, I end up with 1 plus 4n minus 4. And that gives me 4n minus 3. Okay, so that's my sequence definition. I'm going to put that right into my sigma notation. But remember, I'm going to use an I because it's going to be all the terms. Well, you know what? They gave me the number 53. So if I am to formulate this, and I do n minus 1 plus 1 over 2 times, plug the 1 in, and I get 4 minus 3, which is 1. If I plug in into here, I'm supposed to get 53. That's what it tells me. So I could really work backwards and say, I know that 4i minus 3 is equal to 53. So then what was the value of I that I plugged in? Well, 4i equals 56, and I equals 14. So I am going to replace that in my formula with a 14, which means I'm going to replace this with a 14. And so I can now find the sum of those 14 terms. And the way I do that is to simplify here and have 7 times 54. And that answer is 350 and 28 is 378. So how did I do this again? They gave me a sequence. I found the definition of that sequence. I wrote the sigma notation from 1 to whichever term that was. I determined whichever term that was based on the term information they gave me, and then I plugged into the formula to get the sum of that sequence, or the series, is 378. You now have 2 worksheets to explore problems on your own to determine if you can solve a series in finding the last term, or what is n, or what is the sum, using this same formula that I've given you today.